Swayam Prabha. Digital India. Educated India.
Welcome back everybody for the next session, right. So in the previous session we have been looking at Laplacian matrix, right, and we also saw some properties about Laplacian. Okay, so in that direction we will continue. So I'll try to do with an example. So let us start with this graph here. So can you give me the Laplacian of this graph? So let me just start labeling it. So 1, 2, 3, 4, 5, 6. So how do we write the Laplacian matrix? So if there is an edge between I and j, then you write it as -1. If it is not, then I mean this is an undirected graph, so we don't have to take bigger effort, and if there is no edge, then you write it as 0, and when I equal to j, it is going to be nothing but the degree, right. So let us quickly fill this matrix. -1, 0, -1, 0, right. And what about 3? So it's, we can easily see that it is going to be symmetric, so we can just fill it up quickly with this second row. So what about this? Right? Okay. Is this correct or did I make any mistakes? Okay. So why did we do this exercise? So I want to bring out something so you can easily visualize it when you see it. So the idea is, look at a cofactor. You know what a cofactor is, right? Say for any element, what will be the cofactor? Suppose I look at a cofactor of say A11. How do we find the cofactor? Deleting ith row and jth column, you look at the determinant of the remaining matrix, right? That's a cofactor, right? So nothing special. Go back to your basic determinant definition. From there you just bring it out, right? So if you look at the cofactors, what can we say about the cofactors? So obviously we know determinant is 0 for this matrix because we are talking about Laplacian and we know it is singular. Okay. So that's why I am going in for cofactor. We are not talking about the determinant of the whole matrix, but we will talk about the cofactors now. So if you look at any n-1 by n-1 submatrix, say A11 or, and what about A12? I am just randomly picking it up. So what will be the cofactor? Okay, it's a big matrix, so you have to take a little bit of more work here. Can you observe something here if you look at the cofactors? First row, second column, cofactor of 1, 2 if I take, it need not be symmetric, right? If I look at the cofactor, Maybe if you find it too difficult, maybe one half you can do for A11 and the other half try for A12. I leave this as an exercise for you people to fill it up, okay, and see that if you take cofactor, especially for Laplacian, cofactor of any two element in the matrix you take, they have the same value, okay. That's the beauty of Laplacian, okay. So, any two elements in this matrix you take, say A4 comma 6, A3 comma 2, like this, if you pick out any two elements, you will see the cofactor of these two elements are going to be equal, okay. So, there is a very nice principle, so I will leave it now for you. So, you can get a feel for this. As you solve the cofactors, you will see how the rows and columns are behaving, and from there you can get the solution for this. Okay. So, why I did this is we will be using the cofactors more often in proving our other results. So, we will get back to this, and now let us look into this matrix. So, as a refresher, now we will start with look at the n by n matrix formed by some of these two matrices. A times I, the identity matrix, right, on n by n identity matrix, and B times Jn, where Jn is nothing but the matrix of all ones, okay. So, what can we say about the eigenvalues of these two matrices, I mean this matrix Ai plus Bj. So, what do we know about the spectrum of J? We know something, right? We know about all these matrices. So, we can just quickly go through this. So, spectrum of J, we know it is nothing but 0 repeating n minus 1 times and n 1 time, right. So, this is our spectrum of Jn, and so what about B times J? 0 n minus 1 times you will have, and n times B, that is nB, right, or Bn you can say, this would be occurring once, okay, with multiplicity 1, because it is just a matrix, the whole matrix you are going to multiply by B, right. So, if lambda is an eigenvalue, then B times lambda will be an eigenvalue of B times J, right. So, and we know about identity matrix, it has eigenvalue n repeated n times, right. So, now what about spectrum of this Ai plus Bj? So, Ai is going to have the value A, right. What is the spectrum of In? 1 n times, right, I am sorry, I said n times, 1 n times, right. So, now A times I is going to be nothing but the spectrum is going to be A repeated n times, right. So, now spectrum of Ai plus Bj, if you see, this is going to be nothing but A repeating n minus 1 times and A plus nB repeating or having a multiplicity 1, right. So, now from here we will pick up the graph class that we want. What about complete graph? So, this is one result, that eigenvalue of an n by n matrix A times I plus B times J is nothing but the value eigenvalue is A with multiplicity n minus 1 and A plus nB with multiplicity 1, okay. So, now with this let us think about Kn. So, what is Kn? What is it? How does the Kn matrix look like? J minus I. I am talking about Laplacian matrix, we are not talking about identity matrix, adjacency matrix, I am sorry. We are always, now we are in Laplacian matrix, right. So, yeah, I should have mentioned that here. So, spectrum of L of Jn is what we are looking at everywhere. So, we started with Laplacian. So, now what about this L of Kn? So, off diagonal elements are going to be minus 1, that you know every off diagonal element is minus 1, and diagonal n minus 1, right. So, if I want to write it in this language, can I rewrite it as some A times I plus B times J, Ni minus J, is that okay? So, this is answer he has given, I do not know, I am just writing it. I minus j. So, j has all ones. If diagonal 1 is subtracting, then you get all diagonals n minus 2. Kn matrix, the Laplacian of Kn is nothing but Ni minus j. So, now from the previous result you can immediately conclude the spectrum of the Laplacian is n minus 1 times and n plus or plus n times of minus 1, right. So, n minus n, which will be 0. So, n occurs n minus 1 times and 0 is with multiplicity 1, right. So, we know obviously there is a 0 eigenvalue which should be coming in our Laplacian, because the graph is connected and we need to have a non-singular matrix here, right. So, now in similar direction, what can I say about L of k m n? So, obviously I know it is not going to be immediate, but okay, let me put forth a different thing before we come to L of k m n. Suppose we have a graph G, okay, with the Laplacian spectrum and we have the Laplacian matrix, and the spectrum of this L of G is given, say let us just take a generic case, say it is lambda 1, lambda 2, I just give an ordering to it, lambda n, and I know only that my last value is 0, right. I have just loosely written here, I am just trying to say that we have n eigenvalues and they are ordered in this fashion, okay. Yeah, okay. So, now my question is, what can I say about L of G plus A times J? See, we have a matrix which is a Laplacian matrix of some graph. To it I am just going to add A times the J matrix, okay, all ones matrix or all A matrix. Now it would become A times J is all A matrix, right. So, what can we say about the spectrum of this if I know the spectrum of L of G? Can we prove it? I mean, it is quite easy to prove. So, we know L of G has this spectrum lambda 1 to lambda n. What about J? Zeros followed by n, right. J, we have been seeing that, right. So, there is a connection between these two, and how do we connect them properly, right. We know we have been in some places we take directly the sum of these elements in some order and we just write it, right. So, the answer is the spectrum is same as lambda 1 up to lambda n minus 1 followed by n times A. Okay. The n times A comes from the J matrix. So, how do we prove this? So, let us start let us try to prove this. Suppose I have the usual way of proving about eigenvalues is you go into the orthogonal matrix representation and you try to look into the PAP transpose or PMP transpose form, and you know it is going to be nothing but diagonal of all eigenvalues, right. So, we will start from there. So, suppose P is an orthogonal matrix. So, by this what do I know? Every column of P is orthogonal to itself, right. Any two columns you take, they are going to be orthogonal also. So, we know that P LG P transpose or P inverse is nothing but the diagonal matrix of lambda 1 to lambda n, right. In that order, we will fix this order. So, you will get it in this, I mean if you fix the vertices accordingly, you can see that it will be this order. Now, what can I say about J times P matrix? So, let me also be specific here, what kind of P matrix I want to choose, okay. So, let us choose the orthogonal matrix P such that the last column, okay, that I want to look into, it should correspond to my 0 eigenvector of my J, okay. So, that is why I had taken, that is why I am considering this lambda n to be sitting in the last place. So, we have seen already how the eigenvector of 0 eigenvalue for L of G is going to be, right? If my G is a connected graph, then I know how it is going to be, right? So, we will start with being a connected graph, then we will see how it turns out. So, we know how is my eigenvector going to look like for my 0 eigenvalue, for this eigenvalue, all ones, right? That is, we know the components of this eigenvector are all going to be equal, right? So, in particular, let us choose the matrix, the orthogonal matrix with the eigenvector, say 1 over root n. In place of 1, we know the last eigenvector corresponding to 0 is going to be having all equal components, right? All x1, x2, xn in that vector is going to be equal. So, let me choose a particular choice so that it is easy for me to make this computation here. So, let that choice be 1 over root n, because any constant multiple of 1 is also an eigenvector. So, 1 over root n, the vector with all 1 over root n's is also going to be an eigenvector for 0, right. So, now with this P matrix, okay, what can I say about the product JP? Because I mean all these are going to be columns, they are all eigenvectors again, right, and we are talking about the matrix all ones into P, the P matrix or P transpose. It is an n by n matrix, we can also write it the other way around, right, P or P transpose. So, I have started with P. So, let me write it as P transpose, right. So, what can we say about this JP matrix? You take any row, you multiply with the P matrix, P column matrix and so on. If you see, since we have all the orthogonal vectors, the JP matrix take a very specific form here, which is going to be nothing but all zeros in the first n minus 1 columns, okay, and the last column will only exist for JP, right. So, that would be nothing but, it is going to be nothing but n into root n, right, n times root n, you will be adding 1 over root n plus 1 over root n plus 1 over root n. So, it would be n times 1 over root n, which is root n, and every element in this column will be having the value root n, okay. So, now if I multiply this, pre-multiply this with the P transpose matrix, okay, since we have all 0 here and the last column alone exists, my P transpose will have only my last row existing over there, right. Every other column, if I multiply with this, it would vanish. So, I can immediately see that this P transpose JP is going to be nothing but diagonal of all zeros with n, okay. So, this is where we end up with the eigenvalue. So, now if I just want to extend my argument with the, so I have an A times J, so A times J would be n times A here. So, this would be nothing but, now we are in an ordered setting. So, this means what? I know P transpose L of G into P is a diagonal matrix, right. Similarly, P transpose AJP is again a diagonal matrix with NA on last entry of the diagonal. So, if I add two diagonal matrix, what do we get? We will just get lambda 1, so diagonal of lambda 1, lambda 2 until lambda n minus 1, and the last entry would be nothing but replaced by NA, right. So, therefore, if I know a spectrum of a Laplacian spectrum of a graph, okay, then some A times J, if I add to that, I know what my new spectrum is going to be, okay. So, why are we doing this? I can, when I have A times J, I try to manipulate with the whole graph. I can add some edges, delete some edges, or I am doing something on the whole graph which will elevate me to easily find the spectrum here. So, let me tell you now what we want to do here. Let us consider this complete graph. We know the spectrum of complete graph, I mean Laplacian spectrum, right. Now, from this graph, let us say remove P disjoint edges. Okay, just disjoint edges out of my complete graph I am removing, say edge set like E1, E2, EP. So, where all of them are disjoint, okay. EA and EJ are disjoint, that means what? They do not have a common vertex, right, by disjoint edges or independent edges we say. So, now can we say something about the spectrum of this graph from my existing expression. So, for definiteness I can just start removing, because Kn has every edge is going to be equally likely. I can start picking up vertices in a particular order. Say suppose my E1 is the edge 1, 2, and then E2 I can just remove 3, 4. Like I just need to pick out P edges, right. So, I will keep on removing this. Since we are removing P edges, I will go up to 2P minus 1 comma 2P. So, if suppose I remove all these edges, how is my matrix going to change? My Laplacian matrix previously it was Ni minus j, right. Now, I am removing these P vertices, and I have taken this very specific format just to make our computation easy, right. So, what can we say about my new matrix? How is it going to look like? The removal of this edge 1, 2, where does it affect? In the matrix, in my Laplacian matrix. So, suppose I have my Laplacian matrix, I know it is Ni minus j, right, or in simple terms I know it is going to be n minus 1 along the diagonals and minus 1 everywhere else, right. It is a minus 1 in all upper and lower triangular matrix, I will have everywhere minus 1, right. Suppose I remove this edge 1, 2, where will the impact be in this matrix? Yeah. So, only if you look at this 2 by 2 submatrix, the impact is going to be only over there, right. What will be the impact? So, your degree changes to n minus 2 and here you will have 0, right. So, now similarly I can see this impact happening in every 2 by 2 block in my graph, in my matrix. Every 2 by 2 block of like the P blocks, the first P blocks will have this impact, right. So, we'll be getting a block matrix looking like this, right. This will be of order P, and after this what will be there? From 2P plus 1 to n, the remaining set of vertices, they are not disturbed, right. They are not disturbed in the whole. So, as a block matrix if I see, what will it be? Okay, look, think about it. So, now let us go back to this result. We were talking about L of g plus A of j, right, A times j. So, let us go into this L of g plus, say I take A equal to 1, just J matrix if I add to this given matrix, this G, which is now obtained by Kn minus P disjoint edges, right. You remove the P edges. So, in this graph what was happening? L of g plus j. So, everywhere else of this matrix I had minus 1. So, when I add plus j, that means what? I am adding a plus 1, right. Throughout I am adding a plus 1 to every element of the matrix. So, everything else will vanish now, right. My matrix would now look like 0 everywhere else except all these 2 by 2 blocks, right. 1, 2, 3, 4, 5, 6 and so on until 2p minus 1, 2p. After that there is something happening again, right. What is happening to this lower block? N into I, right. It becomes, because it was previously n minus 1 followed by minus 1 everywhere, right. So, now when I add j to it, now all these entries become n and these would also become 0, right. It is a block matrix of ni here in the of order n minus 2p, right. And in each of this block I get n minus 1, 1, 1 n minus 1, right. So, each of this block is going to look like this, and the last block would be an ni block, right. So, if I want to find the spectrum of this, so the spectrum is going to be coming, I mean it is going to be contributed by each of these blocks, because the other entries are 0, only the spectrum is coming from a block matrix, block diagonal matrix, right. So, what is the spectrum of these block diagonals? Determinant of each of these block diagonals, right. So, we will be getting my L of G plus I would be nothing but this block matrix. So, the spectrum now changes to, so what is the determinant of this 2 by 2 block? N minus 1 the whole square minus 1 you have, that is nothing but n square minus 2n, the constant term vanishes. So, you will just have n into n minus 1 equal to 0. So, if you try to solve this, what are the spectrals that you get? Did I miss something? N minus 2, sorry, yeah, n minus 2, right. So, if I solve for this determinant, this 2 by 2 block, I get this value, right, which is nothing but the spectrum would be nothing but 0 and 2, right, and this appears p times, right. And what about the last block? Ni, how many times this is going to be appearing over here? So, this n block appears n minus 2p, right, n into I of order n minus 2p. So, now what can we say about the spectrum of L of G plus I, right? We were talking about this smaller blocks now. So, from the previous result, I can say that my spectrum should be here. So, my spectrum is going to be the spectrum of L of G, the first n minus 1 spectrum followed by Na, right. So, if I just carry it over there, what do I get? So, now we have to look into the L of G properly, right. My L of G was at the beginning, where are we standing actually? You should just tell me there. Okay, I will give you the answer, you can think about this. So, n minus 2 appearing p times and n appearing n minus p times, because there is a 2 over here. So, okay, I did not tell you what the spectrum of this L of G, right. From there then it would have become easier. So, spectrum of L of G was, since we have removed only p edges out of it, we will be having n minus 2 appearing p times and n appearing n minus p minus 1 time and 0 appearing 1 time, okay, because we are having a Laplacian matrix before manipulation, right. L of G should be having obviously an 0 eigenvalue. So, you can just work it out, you can see that the spectrum of this L of G is this, okay, n minus 2 as an eigenvalue will appear p times, because we have removed the p edges, so that impact will be there, and for the remaining edges it would be n, the n will remain as it is, right, because Kn had n as an eigenvalue n minus 1 times, right. As I remove an edge, the impact is seen in the eigenvalue here, okay. So, now from here L of G plus I will take the expression in this form. So, we have seen that the eigenvalues are 0 and 2, right. So, if I again look at the order, we are looking at the non-zero eigenvalue, so that would be 2. So, from here we can immediately conclude this.